There we go. All right. So, as you may well have noticed, the exams are graded and posted, but I've got a couple of outstanding exams left, so we don't get the physical exams back quite yet. Probably still will do some sort of exam correction thing, but I'll sort that out when we get it all sorted out. So, we have learned all sorts of ways to figure out different stresses. We can pull on something, we can twist on something, we can bend something, we can shear something, and in theory we know all of the associated formulas to figure out the appropriate stresses, and we now can start visualizing what happens if we push and twist, or bend and pull, or whatever. This is the combined loading. And so far I've said, oh, we can't add normal stresses and shear stresses. They cannot. You have to keep them separated. And the 8 pages that I hope to get through today is the first step on how to account for normal stress and shear stress in the same material at the same time. If you think back to part 2, I believe it was, and these different glue joints. This is when we kind of started talking about shear loading. And if we glued this the 2 different ways, in this way, that glue was only experiencing normal stress. The section is perpendicular to the applied force. It's all sigma. But if we oriented it this way, because you've got your normal force that's always normal to the surface, but that's at an angle to the applied force, you end up with a little bit of shear and a little bit of normal. But it's the same basic structure with the same loading. Just the fact that now you're looking at it this way, suddenly there's shear stress and normal stress in the same material. How does that work? It's a little disarming at first, perhaps. It is dependent not only on the geometry. Our geometry and our loading are the same in these two, but it's also dependent on the coordinate system. So what we're going to learn how to do is transform the coordinate system, and then we're going to look for the angles where we don't have any shear, because then it's accounting for the fact that I have normal and shear, but I can move my coordinate system around and figure out where there's a 0, and then we're going to have a normal stress that accounts for both of them. And if that doesn't quite make sense, roll with it, do the math, and hopefully you'll see that it does jive. So basically, we start in with our little cube of stuff. So far, mostly, we've had only one stress going on in our cube of stuff at a time. Either we've had normal or we've had shear in one direction. Really, you can have a pretty complicated thing going on. In 3 space, you can have normal stress that is normal to all of the surfaces, and we call that a sigma x, a sigma y, and we'll say z is coming at us this way. And then we also have shear stresses that act, and if we say this face, and the shear stresses go by a 2-letter subscript. So if I have this one, I have a tau that is on the x face in the y direction. That's why it's that's the subscript convention. And so it has to have an equilibrium friend on its other face that would then be tau on the y face in the x direction. All right. So now we're going to go with a different color. We need to have one that is this guy. So this guy would be tau on the z face in the y direction, friends with tau on the y face in the z direction. And then we need to have one more. We've got this guy, which would be tau on the z face in the x direction with his friend tau x z. It gets pretty messy and complicated pretty quick. And that's just three faces. You've got the other three faces that are the negative. So, woo, it's a lot. And so this stress state, this full stress state, is what you call this second order tensor quantity. And again, tensor is basically indicating that it's a collection of values that are both a magnitude and a direction. So it has 3 squared. If you're in 3 space, it has 3 squared values, and essentially we can do this transformation process that I'm going to take you through the setup for that. So we can put it into a matrix form where we've got our normal stresses along the diagonal. It is a diagonal matrix, and we populate the rest of it, and you'll see that it is symmetric, that here we have tau xy, well here we have tau yx, xz, zx. It's symmetric about that diagonal. Now, because of equilibrium, the red ones have to be equal in magnitude. The blue ones have to be equal in magnitude. The green ones have to be, no, not the green, whatever other color I've got going on up there. So we can say that yx, those two are equal. Xz is equal to zx, and yz is equal to zy. So that simplifies our life, making the subscripts, again, it is now truly a symmetric matrix about that diagonal of normal stresses. So the normal stresses along the diagonal and symmetric along that diagonal. All right. Pretty much so far, if you think back to the couple of combined loading examples that we've ended up with, what have we had? We've had our little cube that has had a normal and a shear. We haven't had a full three-dimensional stress state, and in here we are only going to briefly touch on one case, and that one case is a thick-walled pressure vessel that we'll talk about shortly. But we mostly have one normal stress, one sigma, and one shear stress, or a sigma x and a sigma y. That situation where the rest of them are zero is a very important case that we call plane stress. And basically that's saying that our sigma z is 0, our tau xz is 0, and our tau yx is 0. And if you look at what that's going to do to our matrix, it simplifies our life immensely down to this nice little 2 by 2. So we have, at most, in this class, other than the thick-walled pressure vessel, we have a 2 by 2 that has a normal stress in X, a normal stress in Y, and our one shear stress case. This is called plane stress.
The shear in Z is also 0.
Right.
The normal stress in Z is also 0.
Normal stress in Z is 0. Yep. So we've simplified it down to this 2 by 2. All right. Now hang on to your geometric hats. So we've got our sigma x and our sigma y in some coordinate system that makes sense on our structure. Maybe we've loaded it in the x direction and we have x and y, or whatever. Those are not necessarily the coordinates at which these stresses are maximized. So what do? We need to be able to transform a stress state into some other coordinate system. And we define that if we say we have our original xy system and we want to move it by theta to an x prime y prime. We're going to start with our little cube that is plane stress, which is these simplifications that we've just made. And this over here is the picture of plane stress. It's a whole lot easier than that first little porcupine-looking thing that we drew a minute ago. We've got a sigma x, and also the sigma x on the other side. We've got a sigma y, and then we've got our tau xy. It's called plane stress because all of that would fit on a piece of paper. They're all in the same plane. Sigma x, sigma y, and the taus are all coplanar. So that's why it's called plane stress. All right, now what we got to do to build this stress transformation mathematical construct, we need to take our cube and we're going to slice it on an angle. We're going to slice it on an angle that's equal to this theta that we want to be able to transform, and we're going to do a force balance. So on the left face and the bottom face, you've got what you still ever had. You have a sigma in the y direction, you have a sigma in the x direction, and you have your, and you have your shear on the bottom and the back. That's just like this right here. We've just sliced it along that diagonal. Now, what we have new is the fact that we're going to have a tau x prime y prime that's along our newly sliced face, and we're also going to have a normal in our new x prime direction. So this guy is normal stress in new x prime direction, and this guy is shear along the new face in the y prime, the new x prime face in the y prime direction. All right, everybody with me on my slice now? So now we've got a wedge that we're going to do a statics problem on. Okay? What do you do a statics problem with? What do you need? You need the sum of the forces. This picture has what on it? Stresses. How do we get from stress to force? Multiply by area. So we need some geometry on our little wedge, because force is stress times area. We need the areas. We're going to call this width W, and we're going to call along this face, we're going to say that is 1 unit of long. So this front face, the area is W times 1. All right. How about if this is 1 and this is our theta, this guy has to be cos theta, and this guy has to be sine theta. All right? So my back face...
Can we do this with matrices multiplication and like, it's like cosine theta, sine theta?
That's what we're going to end up with. This is building that transformation matrix. This is going through the geometry of where those cosines and sines come from.
I just want to see this one.
Yep, that's exactly where we're going. So that area on the back face is what? Is W cos theta. Area of the back is W cos theta. And then how about the area of the bottom? Is W sine theta. Y'all with me? All right. So then our stresses are our forces are our stresses times our area. So this guy has to be our stress times our area. This guy is our stress times the area. And this guy is the stress times the area. All right? And then same thing follows for our shears. The one along the face is tau x prime y prime w. This guy along the floor, tau xy w sine theta. And this guy along the back wall, where do I have room? Down here is tau xy w cos theta. All right? Those are my forces. Now, I need to sum them in my new coordinate system. So I'm going to need components of these that are in the old orthogonal xy. All right, this gets a little bit messy, so we're going to do our normal ones first. So right now we have this guy that is in the correct direction. And we have this guy that is how big? He is sigma x w cos theta, right? That's the original. I'm putting him in dots because this is the one that we have to figure out the components of. And this guy is sigma y w sine theta. But what we need is to resolve this guy into an x prime and a y prime component, and we need to resolve that guy into a y prime and an x prime component. And that's our theta, and that's our theta. So this one here, sigma y w sine theta times, that guy is going to be times cos theta, and this guy is sigma y w sine theta times sine theta. I know. What's this guy? Sigma x w cos theta times cos theta. And this guy is sigma x w cos theta sine theta. And this is posted in its entirety, but in the interest of getting through it all, I mean, I think you all are seeing where it's coming from, and along here, we had tau x prime y prime times w. And then we have one that's along this bottom surface that we need to resolve into those two guys. And we have one along the back surface that we need to resolve into those two. And this is tau xy w sine theta. That's the original magnitude times cos theta. Tau xy w sine theta sine theta. Oh. Tau xy w cos theta sine theta. Tau xy w cos theta cos theta. So all of that lets us get to the point that we can do the equilibrium problem. All right. So I'm going to try to put this over here small enough so you can at least kind of sort of see where the equilibrium problem is coming from. Okay, there's our 2, and then we need this guy on this side. And we need to get down to our force balance. All right. So, going to start with our purple components. We need the sum of the forces in our x prime direction. So, we have a sigma x prime times w is this guy. Can you see the mouse on there? All right, so we need now a minus that guy and minus that guy. So minus sigma x, w, and that's a cosine squared theta, and a minus sigma y, w, sine squared theta. And now we go grab the stuff off of the shear. What do we got in the x prime direction? We just have 2. And they're both minuses. So we have a minus tau xy, and these are cross terms, cos sine, and another minus tau xy, w sine theta, cos theta. And all that equals 0. Well, we see one thing, w falls out. And what do we actually want? We actually want our sigma x prime. We want to know what our stress is in our new transformed coordinate. So we can now solve this guy for our sigma x prime, and that is going to equal all of the rest of those other terms go over on the other side and become positive. So we have sigma x cos squared, sigma y sine squared, and then we got 2 of these guys, plus 2, tau xy cos theta sine theta. All right? Still with me? Kind of, sort of? The details are details, but you're with me fundamentally as to what we're doing. And again, the details are posted already correct and hopefully with no typos and rightos. What else do we got? Now we got to do...
I was about to say.
So I was hoping for some less trivia after this.
No.
I was looking that way.
We get one little trig trick. It's not even really an identity, but we do one trig trick in just a second. So now we need to sum in our y prime direction. So what do we got in y prime? We have starting here, we've got this guy is a plus, so plus sigma x, and that's a cross term, w cos theta sine theta. And then we've got this guy minus sigma y w cos theta sine theta. Is that all that's going on in the y prime direction on this guy? Yep. All right, now we got stuff off the shear. And we have three things. We have the plus that's in our x prime, y prime. We have this minus component, and we have this plus component. So I'm just going to kind of continue it down here. So plus tau x prime, y prime, w on our cut face, and then a w cosine squared. That's this guy. And then we have a plus tau xy w sine squared theta equals 0. Okay, this guy is the one we really care about. So tau x prime y prime is minus sigma x cosine sine plus sigma y cosine sine plus tau xy times cosine squared minus sine squared equals 0? No, wait. All of this equals 0. That doesn't equal 0. Okie dokie. So now we have two equations. We have an equation for our sigma x prime. We have an equation for our tau x prime y prime. We're still missing one. We need our transformed y normal stress. We need our sigma y prime. And this is where a little trig trick comes in. If we have this transformation thing happening, if we start with an xy and we rotate to an x prime, y prime, and we know we've gone theta here, well, we know that this guy has to be theta plus 90. That's just because it's still an orthogonal axis. So here's our one little trig trick. We know that cosine of something 90 degrees more than theta is minus sine, and we know that sine of 90 degrees past where we are is cosine of that thing. So with that trick, we don't have to do our force balance again. We can just say sigma, we can just say, drat it, sigma y prime is then sigma x sine squared theta, sigma y cos squared theta minus the shear times the cross term. Then we can pull those equations into matrix form, and I guess we can now zoom it back up so you can actually kind of see what in the world is going on here, although you have that on yours. So yeah. So now we collect these three that we just did all of this sum of the forces business. We collect these into matrix form. So like this one right here, sigma x prime, we've got sigma x times sine squared. You got to remember how your matrix math works. We got sigma y times cosine, and we have a minus 2 cosine sine. That creature is our transformation matrix. So I can give you any arbitrary, what is this thing right here called? That collection of sigma x, sigma y, tau xy? No. No. This is your stress state. So yeah, not talking about the math of it. What is it in here? This collection of sigma x, sigma y, one normal stress in your x direction, a normal stress in the y direction, and the shear stress. If I scroll back up, that is, that's this picture. That is your stress state. And so written vector form, that is sigma x, sigma y, tau xy. That's what that is. Okay? So now if I scroll back down, if I say, or if you solve a problem, hey, that moved. I'm not even going to try and move it. If you solve one of the problems and see, okay, I end up with a sigma x equals something, a sigma y equals 0, and a shear stress equals something, like the flagpole problem that we did at the end of last time, we ended up with one normal stress and one shear stress. And I say, okay, now we want to rotate that coordinate system by 30 degrees. You just use this transformation matrix. So a sort of arbitrary example is a stress state that is sigma x equals 8,000, sigma y equals negative 3,000, and then the course pack is missing the fact that tau xy equals a plus 6,000. Okay, what does that look like in terms of our little cube of material? It looks like sigma x is this, sigma y is that, and tau, how do I know which way to draw the arrow from tau? Got to remember your sign conventions. A plus tau is when the stress on the plus x face is in the plus y direction. So you draw that guy, and then you draw this guy to match it. So this is what my little cube of material looks like if I draw that arbitrary stress state. All right. So if I then say, okay, x prime and y prime are 30 degrees. I plug in my sigma x, sigma y, and tau xy, and I program my calculator, I program MATLAB, or I'm really sad and I don't have either of these tools and I do this by hand. Whatever. It's matrix math. Remember how to do it. Figure it out. Be happy.
Yeah, remember how to do that.
Would tau x prime y prime be, would it be 6,000, or would those two of them each be 4,000?
No, it is 6,000.
Each one is 6,000.
That's right. Yeah, these are not separate forces. It's the fact that if you've got a shear stress here, you have to have a corresponding shear stress here to keep it in equilibrium.
I'm kind of confused on why you would want to do this. Like,
Hang with me 2 more pages. Okay, so just smile and nod for a second and know that you can do this math with some tool, that cosine squared of 30 ends up being 0.75 and da-da-da-da-da, and you can do matrix math, and you end up with numbers here. And the numbers that you get in this particular case is 10,446, minus 5,446, and minus 1,763. That's my vector of new normal stress x, new normal stress y, and new shear stress tau x prime y prime. So look at those compared. My x got bigger and more positive. My y, what happened to it? It got larger in magnitude, but more negative. And this guy flip-flopped. It was 6,000 positive. It's now 1,763 negative. What do those look like? Okay, so we already kind of have one of them there. The original is 8K, 3K, and 6K. And then if we transform it, we rotate our cube by 30 degrees, we now have 10.4K. We have 5.4K. And again, the stress goes by the plus x prime face, and it's negative in the y prime direction. So my shear stress looks like that. So rotating it by 30 degrees makes that change. What if I rotated it by a little more, 33 degrees, or a little less, 27 degrees, or 80 degrees? You have to think that as I'm moving through all these possible coordinate systems that I can put it in, there's going to be a point that you get to the biggest possible sigma x prime. That is principal stress. That is the number. When you get to that number, that's when your tau is actually going to go to 0. And so this next plot here is the why are we bothering. Okay? So what is theta equals 0? Theta equals 0 is where we started. That's this picture right here. So check it out. We've got sigma x prime, the transformed one, is blue. Sigma y is red, and tau is the green. Okay, so what is our stress state at theta equals 0, untransformed? It's plus 8,000, plus 6,000, and minus 3. That was what we started with. Now, what did we rotate it through? When we just did our little transformation, what did we do? We arbitrarily picked 30 out of thin air. And if we come over to 30 and look at what's going on at theta equals 30 degrees, what is it? Hey, look, these numbers should look familiar. What did we just get? We got 10 for something, something, something. We got minus 17 something something, and we got minus 5,446. Is the picture starting to make sense? All right, so now if I wanted to know where my biggest sigma x is, how far do I rotate to get to my biggest sigma x, what do? Well, I went a little too far. I need to back it up. I need to back it up to there. And what happens when you go to the max? The max of sigma x prime corresponds to the 0 crossing of the shear, and it corresponds to the negative extrema of the sigma y. This is how you account for the fact that at some arbitrary analysis point, you might have sigmas and taus in your answer. You look for which rotation angle is the maximum. Those are principal stresses.
If you took the sigma y and sigma x prime and took the magnitude, would that give you like
like Pythagorean resultant? Yeah.
Because the extremists for the sigma x and sigma y, like when sigma x goes to negative, sigma y goes back up to positive, but they're equivalent. Their maximas and minimums are equivalent.
You're talking about current the same angle.
Yeah.
Or the shift, when it shifted.
It seemed like they occurred at the same angle.
Well, right, if you go 90 degrees, then yes, they flip-flopped. Yes. Is that what you were asking? Because that's different than Pythagorean distance.
I was wondering, like, if you took, like, if you did the square root of the sum of the squares and got that magnitude, would that be like a maximum stress?
Almost. Again, hang with me another half a page. Because we end up, it's the square of the difference.
Okay.
So, what are the things that we see that are notable? At about theta equals 25 degrees, sigma x prime is max, and sigma y prime is min. We've already discussed that. Then what happens at 90 degrees beyond that? At 25 plus 90, they swap. Okay, the other important thing that we've already touched on, if sigma x prime or sigma y prime is at a max or a min, the shear is 0. And where is it that the shear is maximized? It's at plus or minus 45 from the others. So if you look back here, at the point that shear is maximized, your normal stresses are equal. And that happens 45 degrees. So tau x prime y prime is max or min at plus or minus 45 degrees from sigma x prime, sigma y prime, max or min. And where tau x prime, y prime is max or min, sigma x prime equals sigma y prime. So I will take a second to let you write those things down because those are the important things to realize about this whole stress transformation thing. And then the last thing is pulling the equations out so that we can do this stress transformation and just jump to the chase and say, what is the biggest sigma A? What is the biggest sigma X, rather? And we're going to call them sigma A. All right. All right. So if we have this expression, which is the thing that we got from our geometry, how do we figure out where the maximum is? What's the calculus default of finding a maximum? We want to do derivative with respect to theta of sigma x prime and set it equal to 0. Now, we ain't about to go through the time because that's when you start getting your trig identities and all kinds of ugly things, and we ain't got time for that. So, jumping over all of that, we end up with the fact that one of these angles is 1/2 the inverse tangent of my original shear over the difference, over half the difference of my original normal stresses. And that's tangent, not tau. And the other angle is 90 degrees from that. Okay? If that's our angle, if that's our theta that maximizes it, what we do to get our max value, we take this guy and substitute it in here to figure out what our max value of sigma x prime is. And skipping over a little bit of the painfulness, we find that our max sigmas are the average stress, plus or minus. Here's what you were trying to do. The difference squared plus the shear squared. Put a star, question mark, neon sign on the fact that these two quantities are not the same. One of them is the sum, is the average, and one of them is half of the difference. Those are not equal. Very, very common malfunction. All right. So now, if we go back to this example that we've been working with, this arbitrary stress state that looks like this, we can jump over part of what we did and just say, what are the principal stresses? We have sigma x, and that still doesn't have tau xy equals. So we can cut to the chase and say our principal stresses, sigma A and B, and that's a notation. Sigma x and y is an arbitrary stress state. When we do this and find our principal stresses, we call them sigma A and B. So sigma A and B, principal stresses, what do we substitute in? We have sigma x, 8,000, plus sigma y, which is minus 3,000, over 2, plus or minus the square root of sigma x minus sigma y over 2. Did y'all just see that move? It turned into a swishy thing. That thing squared. And what else goes under here? Plus 6,000 squared. All right. So we get sigma A and B equals, that average is 2,500, and we get a plus or minus 8139 psi, which is 10,639 and minus 5639 psi. And those are just a little bit bigger in magnitude than our arbitrary pick of 30 degrees. These are principal stresses.
I get the, okay, so that's like your maximum and your minimum.
Mm-hmm. And if I rotate through this angle, and I haven't figured out the angle yet, let's figure out the angle. Where does that happen? It happens at theta A, which is 1/2 the inverse tangent of, what do I put in? Tau over the difference divided by 2, and that ends up being 23.75 degrees. And theta B, 23.75 plus 90 is 113.75. So if I come back here, it is 23.75 degrees is that location. All right, now back to your question. Did you not leave a question hanging?
And I was just saying, that's your maximum.
Yes. That is that number and that number.
So it'll always be sigma x first. So I mean,
Well, it's vice versa because sigma y will reach that value when the
in terms of sigma A and sigma B, it actually doesn't matter because it's all circular.
Okay.
We will learn another way to rank principal stresses that ranks them from biggest positive to smallest negative. So sigma A and sigma B, it doesn't really matter. When we then cast them as sigma 1, 2, 3 principal stresses, then the biggest positive one is sigma 1, da, 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 da. And that leads into failure criteria. You have to rank them by magnitude and sign to plug them into failure criteria to get the factors of safety. Cool.
That's what we use.
Yeah. Right.
All right. Excellent.
Is that where we need to get today?
That was precisely how much I wanted to cover today.
So we're going to do pressure vessels.
Now we zip back and cover pressure vessels, and I think I'm just going to reorder the course pack because I think this ends up making it all gel better. That we've seen this because when we do the pressure vessel, that case is a special case where the hoop direction is a principal stress and the axial direction is a principal stress. So we're going to slap strain gauges on this thing and measure biaxial stress in a nice simple case. It's pretty slick, really.
So we'll compare the radicals to
Well, actually, we'll figure out the thickness of the wall of the pressure vessel just by measuring the strain.